Lab 3, Black Hole Lab by Shervin Praveen. The purpose of this lab is to find the mass of one object based on the trajectory of another object orbiting it. For part 2, we want to create a model of a ship orbiting around a planet and its moon. Preview. By knowing the mass of one object, we can accurately find the mass of another object during each delta t. With trial and error, we can create an initial velocity of our ship to perfectly orbit two objects without crashing. Main ideas and principles: the velocity update, position update, and force of gravity formula. Reason for each model. The velocity update. We use this to change our velocity through each iteration. The position update to update our position in respect to the origin through each iteration. And the gravitational formula to measure the force of gravity depending on mass and distance. Initial conditions. Many variables were given with the starter code. For part 1, we were given our distances so we can find the mass from our force of gravity formula. For part 2, we were given the motion of the moon around the planet and the mass of all our objects. The system was the star and the spaceship, and the surroundings were the black hole, moon, and planet. For part 1, we set arrows to depict the direction and magnitude of forces acting on our star. We find that the mass of the black hole is approximately 1.1 times 10 to the 44th kilograms. We find this by taking the average of all the masses from each loop. For part 2, we take into account the forces of the moon and the planet. We find that our speed ends up being 25,000 in the x direction and 25,000 in the y direction with no crashes. That's our initial velocity. This is the coding details. On the left for part 1, we were given our initial velocity, so we had to find each of our forces from change in velocity over change in time. For part 2, we were given the masses of everything, and we had to find the distances by subtracting our positions from the origin positions. For example, the moon's position minus the planet's position, or the ship's position minus the planet's position. After that, we used the velocity update formulas using the net force we found, and then we used the position update formulas using the updated velocities. These are our results. On the left, we have our results from part 1. The pink arrow shows dp dt parallel. The teal arrow shows dp dt perpendicular. And the orange arrow shows the net force. And we have the given mass of the black hole for each loop. On the right shows the results for part 2 in the lab. And when we set the speed in the x and y direction to be 25,000 meters per second in the positive direction, we find that it orbits the planet and the moon without any crashes. And this is what we want, but when we set the x direction to be 17,500 in the positive direction and the y to be 25,000 meters per second in the positive direction, we find an even better orbit of our ship around the moon and the planet. I found it hard to find an accurate answer, and we just did it through trial and error to find what works best. Similarities between real life and the modeled. The motion would be very similar since we are taking into account the main forces, but the difference would come from our assumptions. We are assuming every variable we define is perfect, when in reality it's hard to measure anything perfectly. Our sources of error could come from our model, because our model takes into account only the forces we are focusing on, even though there are many other forces and variables. Research question: what is the difference between the rate of change in momentum and its components and net force? We think of dp dt and its components in its parallel and perpendicular components, and net force as the combination of all forces, but the formulas are the same. dp dt does equal F net. And if we want to predict the motion of the black hole, star, planet, and moon, how would we make a model, and would there be any dominant interactions? To make a model, our F net would be a combination of all the gravity from all of these forces, and there would definitely be dominant interactions because some objects are more massive than others. For example, the black hole is more massive than the moon, so its gravitational force would be much larger than the moon. So the moon would have much less force acting on whatever we want. Thank you.